Imagine the quiet of a laboratory at night, the hum of machines soft as a lullaby, and the neat, relentless logic of engineers strolling between wind tunnels and drafting boards like astronomers walking among stars. In the 1970s, inside NASA's Langley Research Center, a small constellation of ideas began to glow. They were not grand slogans or glossy posters, but patient, stubborn lines of inquiry that engineers followed into the wind. A historian would later call them arcane, even odd, strange hardware, unglamorous topics, but in their strangeness they held the power to change how the world's great airliners moved through the sky. One question, deceptively simple, became a lever. Must an aircraft be made of metal? For decades, that assumption had been as steady as bedrock. Aluminum and steel were the familiar bones and skin of flight. Yet a quiet revolution took shape in threads. Picture a factory floor where, instead of rivet guns and metal sheets, machines feed out clean, shining ribbons from gigantic spools, weaving layer upon layer of strength at the speed of a patient heartbeat. It sounded like science fiction, but by the end of that decade, a reporter peered into that future and suggested that large jets, commercial and military alike, might soon be made not of metal, but of something like thread. The idea felt playful to outsiders and profoundly serious to those in the hangars, because thread meant weight spared, and weight spared meant fuel saved. Fuel saved meant range, economy, and the stamina to endure hard times. If you find this kind of gentle journey into aviation's quiet breakthroughs soothing, float along with us. Like and subscribe to Space Historian so you can settle in each night to another calm story of the skies. We'll keep the tone unhurried and the facts steady underfoot. Another idea from Langley looked not at what airplanes were made of, but at their shape, specifically at the wing tip, where invisible whirlpools of air curl like fingerprints. In the still air of a tunnel, engineers watched those vortices with the patience of gardeners studying a river's eddies. What if the tip of the wing could behave less like a blunt end and more like a sail, catching those curls and coaxing them into something useful? So they stretched the wing upward at the tip, a vertical flourish that seemed at first glance merely stylistic. But it wasn't decoration. It was a small sail on a sea of air, dipping into the spinning currents and nudging them into forward help. Less drag, more efficiency. A little bit of cleverness doing quiet work, minute after minute, mile after mile. In time, passengers would look out and see those upturned tips on aircraft like the MD-11 in the 1980s, without quite realizing they were watching an idea made visible, an answer at the end of a long chain of questions. Then there was the supercritical wing, a shape that seemed to defy what a wing should look like. Even its creator, stepping back from the wind tunnel glass, admitted that no one would embrace it without a demonstration in the sky. It was the kind of concept that made eyebrows rise in the conference room, and yet when it finally proved itself in flight, the skeptics thinned like morning fog. Together, these three developments, aircraft components spun from threads, wingtip sails now called winglets, and supercritical wings, drew the outlines of a different future. They were the backbone of two linked efforts under the Aircraft Energy Efficiency Program: composite primary structures on one hand, and on the other, the energy-efficient transport studies that refined wings and wingtips with a craftsman's care. The ambition was practical: cut weight, reduce drag, and sip less fuel. The effect was graceful: a fleet that learned to do more with less. To understand why this work took root where it did, the story changes altitude and time. It drifts down to the tidewater of Virginia in the summer of 1918, when a young writer walked past a place called the Flying Field. There men wrestled with the marshy earth, prying out old roots, leveling and filling, transforming soft ground into something firm enough to launch dreams. The labour was endless and muddy, the kind of toil a novelist would later describe as a feverish loop. Yet from that labour rose an uncommon institution, the only civilian aviation laboratory in the United States until 1941, and the first centre of a young organisation with a careful title, National Advisory Committee for Aeronautics. They named the field for Samuel Pierpont Langley, a man who had watched the sky not only as an astronomer, but as a student of flight. Long before that field existed, he chased the problem of powered flying machines with an earnest zeal. His contraptions, called aerodromes, were fascinating and fragile, and when they failed, the press found a tidy nickname: Langley's Folly. He died in 1906, his dream unfulfilled, but the laboratory that bore his name would take the long road he began and build it into a map. When the NACA was chartered in 1915, its mission was set down in words that sounded almost modest: to supervise and direct the scientific study of the problems of flight, aiming at practical solutions. Practical, there was the key. The engineers at Langley were not invited to live on the peaks of pure theory. They were asked to put hands on machines, to peer at airfoils in tunnels, and then watch actual aircraft demonstrate those lessons in the wind. There were no illusions about whose work this was. It was the kind of work that turns an idea into a bolt pattern and a bolt pattern into takeoff. By 1920, Langley opened its first wind tunnel, a wooden giant by later standards but a marvel in its day. Those early biplanes, with their wood and fabric bones, were light, and in their lightness they gave engineers the gift of change. Shape mattered. A cleaner wing paid dividends in speed. A well-chosen propeller lifted more cleanly into the morning air. Flaps, moved at the right time, bent the air to a pilot's will. The Langley team built a full-scale propeller research tunnel by 1926, a cavernous lung of air that let them understand how blades bit and breathed. They learned how to tuck landing gear into the body of an airplane, how to wrap an engine in a streamlined cover that kept it cool while it slipped through the wind with less fuss. Scaled models came and went like fish in a current, each one a hypothesis made of wood and paint. In the 1930s, this rhythm began to pay off in aircraft the public could name. The Douglas DC-3, a workhorse that stitched continents together, benefited from tests run at Langley. So did the Boeing B-17, whose broad wings and sturdy frame would later cast shadows over wartime fields. By 1944, the NACA was testing dozens upon dozens of aircraft types, most of them at Langley. But the laboratory no longer worked alone. The NACA had established aims on the West Coast and Lewis in Ohio, spreading its talent like seed across climates and specializations. Propulsion, aerodynamics, structures, each found a home with its particular tools and personalities. After the war, the nature of the questions changed. The sound barrier stood like a taut wire across the plains, and new jets probed it with needle-nosed experiments that wore the letter X like a badge. Rotorcraft rose and settled with puzzling grace, and engineers pondered how to lift not only forward, but straight up. Langley was still crucial, but no longer solitary. The country's aeronautical landscape had diversified. New laboratories, new budgets, new hands on the wheel. The decades that followed reshaped the power structure around flight. After the First World War, the NACA had a crisp vision: improve American aeronautics. After the Second, it had rival institutions and a more complicated map. Jet propulsion had swept onto the stage, and a newly independent US Air Force pursued its own research, flush with resources and urgency. Meanwhile, the aircraft industry swelled into a giant, building its own test facilities and tapping the NACA's best young engineers with salaries the government could not match. Industry's voice grew louder in deciding what problems should be solved and when. The NACA did not stop contributing. Historians would later point to achievements in axial compressors and supersonic theory, but the organization needed renewal. One writer said the agency seemed to be waiting for a match. Another observed that the Air Force was now calling the tune. And then, in 1957, a small sphere crossed the sky and spoke in beeps. The match was struck. With Sputnik's arc, the nation pivoted, and in 1958 the NACA gave way to NASA. Space took the spotlight, but aeronautics did not vanish into the wings. At Langley, aviation research continued, less glamorous perhaps than rockets and moon missions, but vital in a different way. Flight was no longer a newborn technology. The basic grammar of wings and engines was now widely understood, and the military and industry could mount their own research programs. Against the gleam of Apollo, aeronautics often felt like a dependable craftsman working in the next room. Yet it was precisely in that role, steady, applied, industry-facing, that Langley would find its moment again in the 1970s, in a project focused not on headlines, but on fuel, the Aircraft Energy Efficiency Program. The timing was not accidental. In that decade, the economics of flying hardened. Fuel grew expensive. Airlines, custodians of long routes and thin margins, looked closely at the edges of their costs and found that weight and drag were written everywhere. The aircraft industry, massive and proud, was also a pillar of the country's trade surplus, second only to agriculture. Billions in international sales moved through factory doors, and each exported jumbo jet, one manager liked to say, could offset the import of thousands of cars. But dominance is not a birthright. Engineers at Langley could read the signs. Overseas competitors were building efficient airplanes of their own. A deputy project manager spoke of a real threat. The challenge was simple to say and difficult to meet. Build airplanes that burned less fuel without starving their performance. Across the Atlantic, a consortium of European firms had joined to form Airbus, with the explicit goal of shaping a competitor to American-built jets. In the late 1970s, a Langley director even showed a photograph of a French Airbus in the livery of a US airline as a kind of cautionary tale. He spoke too about slowing the outward flow of certain research findings, an awkward change for a culture accustomed to open exchange. The message, underneath the pragmatism, was clear enough. The work Langley did under the energy program mattered both to airline economics and to the country's place in the industry. In lean times, engineering insight becomes more than a curiosity. It becomes strategy. So the ACE work pressed on with two intertwined goals: lighten the airframe and smooth its passage through air. On one front stood Composites, new materials bonded from fibers and resins, promising great strength for low weight. On another front stood Winglets and Supercritical wings, shapes tuned to domesticate the caprices of air at cruising speeds. The payoff, measured in percentage points of fuel saved, might not make a banner headline, but over the life of a fleet it added up to fortunes in fuel and to gentler demands on the planet. To appreciate why composites felt so central, why some called materials the strategic centre of gravity, you can let your mind drift back over the long history of weight in flight. From the beginning, weight was the unforgiving auditor. Early machines leapt into the air on frames of wood and cloth and wire, stripped down to bare essentials by necessity. In the 1920s, a different vision of strength took hold with the Ford Trimotor, the tin goose, shaped from metal and aluminum. Corrugated skins wrapped around truss-like skeletons, turning shimmering sheets into hull and wing. In the following decade, another leap. stressed skin, aluminum monocoque construction, where the skin itself helped carry load. Langley's engineers laboured not only with wind but with mathematics, stress and strength analyses that taught designers how to trust thinner metal and smarter curves. Those lessons would feed into thinner wings for military aircraft in the 1940s, wings that had to bear higher speeds and heavier manoeuvres without tearing themselves apart. New alloys came into service, each a dialogue between chemist, metallurgist and aerodynamicist, and Langley helped show where they could be trusted. By the 1960s, a new kind of material began to whisper its potential. Composites, people called them, a word that simply meant a union, two or more substances joined into one structure. That simple definition hid a wealth of intricacy. In a composite, strong fibers are embedded in a matrix, often a polymer resin that holds them in place. Glass, graphite, and other synthetics supply the threads. The resin binds them into a coherent whole. The geometry can be as austere as flat tapes, or as flexible as thin fabrics laid in layers, each oriented to shoulder load in a different direction. You could build up thickness in gentle steps, like a weaver adding rows to a tapestry, until you had complex curves that would be a nightmare to craft out of metal. The surface came out smooth, the transitions gentle, the weight pleasingly low. For an engineer with fuel burn on the mind, it felt like finding a new verb. In 1967, at a celebration marking 50 years of Langley's life, a few of those engineers allowed themselves to speak of aircraft ideas that sat on the threshold. Materials lay among them like a promise. Consider the scale they faced. The fragile craft of the Wright brothers had weighed about 1,260 pounds. By contrast, the all-metal 747 that took its first flights the year after the celebration weighed on the order of £750,000. Every pound clawed at the fuel budget. Every pound saved was a small truce with gravity. If you could carve weight out of the structure without giving up strength or safety, you would. And composites invited exactly that. It helped that composite components could be coaxed into forms hard for aluminum. Long, smooth sweeps with few joints. Substructures without arrays of rivets. Internal shapes laid up in moulds, where layers of cloth and tape followed contours like fabric over a shoulder. The imagery of thread was not a mere metaphor. Machines really did spool out the fibers from large reels, impregnated with resin, and lay them down in precise paths. The result was a part that looked simple, but concealed an architecture of fibers whose orientations had been chosen to carry loads the way a tree's grain carries wind through a trunk and out into leaves. Skepticism never vanished. Engineers are paid not only to dream but to worry. They asked, how would these materials behave after years of pressurization cycles, after countless thermal swings, after an airline's maintenance schedule had grown comfortable and brisk? How would a mechanic inspect for damage that did not look like a metal dent? How would a manufacturing line ensure consistency across thousands of parts? Langley's answer was to test and to test again. Coupons in machines that pulled and bent, panels in rigs that pressurized and released, components in full-scale demonstrations that could be walked around and examined in the blunt light of a hangar. If the composite story was about weight, the winglet and the supercritical wing were about the way air piles up around a moving shape. At a wingtip, high-pressure air under the wing leaks around to the low-pressure region above, curling into a vortex that trails behind the airplane like a twisting ribbon. That vortex is energy the airplane has spent to create. A winglet is a way to reclaim some small portion of that energy. By turning the wingtip up, the airplane reshapes the pressure difference and the flow, thinning the vortex and, in some regimes, nudging a component of force in the forward direction. It is not magic. It is a set of subtle changes that, integrated over long flights, shave off drag. Passengers learned to recognize them the way people recognize a friend's silhouette, an upward flicker at the end of a wing, sometimes canted, sometimes blended, each manufacturer with its own signature. The supercritical wing, meanwhile, addressed what happens on the top surface of a wing as it approaches transonic speeds. The classic airfoil shape encourages a region of locally supersonic flow that must slow back down, a transition that can bring drag spikes and unsteady behavior. The supercritical profile flattens the top and fattens the rear in counterintuitive ways, delaying shock formation and reducing the penalties near cruising speeds. To the eye trained on conventional airfoils, it looked wrong. To the instruments in a test aircraft, it looked right. All of these strands, composites, winglets, supercritical wings, were braided into projects at Langley with a single aim: energy efficiency. The titles were prosaic: composite primary aircraft structures, energy efficient transport, but the consequences were felt in the fuel numbers. Airlines, sharing in the testing and providing feedback from the line, found ways to adapt maintenance routines, pilot manuals, and procurement plans. Manufacturers learned how to build molds and manage autoclaves, how to design joints between composite and metal. Sometimes the advances arrived at different speeds. Winglets showed up on fleets while composites built their resume piece by piece, but the direction was steady. In the world beyond the laboratory walls, the stakes felt large. The US aircraft industry was not only a symbol, but a ledger item. Exports and jobs, supply chains in dozens of states, pride that arced from airport gates to factory floors. Between 1970 and 1975, American manufacturers sold billions in airplanes abroad. Yet no one in those years could ignore the future bending toward competition. Airbus, in particular, represented more than a single airplane. It was a way of pooling European expertise and ambition. When a Langley director said the centre might share fewer details with European partners for a time, it was a reminder that knowledge is not only a gift, it is a strategic asset when margins are thin and markets are contested. Still, the work inside the programme kept its character. Meticulous, methodical, laced with the cautious bravery engineers learn early. Change but not too fast. Innovate but not at the expense of safety. The wonder was not in slogans, but in the way the numbers moved. Faster here, smoother there, more miles per 1,000 pounds of fuel. Airline crews might not think of the exact shape of a pressure distribution curve on a supercritical airfoil as they filed their flight plan, but the airplane did, every minute, and the result was a little less roar of burning fuel and a little more ease in the climb. In time, composite parts grew from small, non-critical components to primary structures. Engineers examined stiffening ribs and spars, control surfaces and fairings, tailplanes and floor beams. Each success widened confidence. Each lesson learned broadened the palette. A composite rudder here, an aileron there, then an empennage designed with new tools. Simultaneously, wingtips bent skyward and then evolved. Simple fences, blended winglets, scimitar shapes. Across fleets, the cumulative effect was a set of familiar horizons reached on a slightly lighter burn. Behind the scenes, the questions stayed elegantly practical. Would a new composite floor beam handle the life of a cabin, with its cargo loads and human traffic? What repair methods would be certified, and how would crews be trained? What kinds of inspections, visual, ultrasonic, tap testing, would airlines schedule, and at what intervals to catch delaminations or impact damage? For winglets, what load changes did the upturned tips impose on the wing route, and what reinforcements would be needed? For supercritical wings, what manufacturing tolerances were most critical to keep the delicate flow behaviour where the wind tunnel said it should be? Each answer turned into a revision of a drawing, a change to a maintenance manual, a new test. The rhythm was patient and exacting. If you are drifting now, half awake, imagine the rooms where these decisions were made. Fluorescent lights, coffee cups gone cold, a whiteboard with sketches of airfoils and arrows showing flow. The people in those rooms argued gently over decimals, the way sailors argue about knots and currents. In the end, they took their arguments back to the tunnel or the prototype and let the wind choose. And when the wind chose, it often favoured the ideas that cut waste. Fuel is discipline made liquid. Save a percent here and another there, and across the life of an aircraft you have returned millions to a balance sheet and spared tons of carbon from the air. No miracle, just the slow harvest of careful thought. The story of Langley is stitched with such harvests. It began in the muddy ground of a flying field, crept through decades of wind tunnel work, surged during war, found new pathways in the X-planes, and then, even as rockets stole the headlines, kept tending the steady fire of aeronautics. When an energy crisis bit into the calculus of flight, Langley was already there with studies, designs, and the humility to test what it thought it knew. It is a comforting thought, perhaps, as you settle your head into the pillow. Somewhere, someone is always walking a model down a hallway toward a tunnel, hearing the whir of motors and the thrum of air, and wondering what the flow will say today. By the late 1970s, as airlines weighed new purchases and manufacturers sketched the next decade's products, the ACE program stood not as a single invention, but as an ecosystem of improvements. There were budget lines and milestones, yes, but all of it came to serve two words that seemed small until you tallied their power: weight and drag. Reduce them, and everything else, range, payload, cost, became a little kinder. The most vital of those initiatives, many thought, was the work on materials, because materials speak to everything an airplane is. Bones and skin, the way it ages, the way it carries its own strength aloft. So the engineers returned to composites again and again. They drew on experience from the early days of metal aircraft, when lessons in stress and strength had allowed so much to be done with so little material. They remembered the shedding of corrugated skins for smooth, load-bearing shells, and they cast the new work in that same spirit, not a rejection of metal, but an evolution in how structures carry the loads of flight. Higher strength alloys had once made possible thinner wings that cut the air with new authority. Now, woven and bonded fibres might deliver the next leap. In the press releases and public explanations, the language was simple. A composite is two or more materials combined. In aircraft use, that means strong fibres, graphite, glass, and their synthetic cousins, bound together in a polymer matrix, often an epoxy. The pieces look like fabrics, thin thread cloths you can drape and layer, or flat tapes you can run in straight lines and gentle curves. Lay them along the lines of force, press and cure, and what emerges can be a component of remarkable stiffness and strength, with the grain oriented exactly where the airplane will ask for it. From these ingredients, engineers could craft surfaces free of rivet lines and joints, contours that the air would caress rather than stumble over. It is no wonder then that some imagined an almost fanciful future as these materials took hold. The phrase that made the rounds, half as a joke and half as a prophecy, was that one day we might see the jet fighter made of thread. Think of a material that feels almost paradoxical, stronger and stiffer than the metals that once defined flight, yet lighter on the scales and gentler against the slow gnaw of corrosion. That promise, wrapped in fibres and resins, made composites irresistibly attractive to aircraft designers. But attraction was not adoption. In the early years, doubts hovered like ground fog. Could these new structures truly endure the crushing cycles of pressurization and the flex of wings in rough air? Would the cost and complexity of designing, testing, and certifying them ever pay off on the production line? And most unsettling of all, how would they age? How would crews maintain them? And what would the record of their durability look like after years in service? As one observer put it plainly, embracing composites in the places that mattered most would require nothing less than a revolution in how aircraft structures were conceived and built. That revolution gathered its first momentum in a 1972 joint effort between the US Air Force and NASA, a long-horizon planning study for composites known as RECAST. Its early successes helped lift composites into the heart of NASA's Aircraft Energy Efficiency Program as one of 6 main pillars, under a name that declared its ambition without fuss: Composite Primary Aircraft Structures. Langley Research Center, with its decades of experience in structures and materials, would oversee the work, flanked by industry partners who built the airplanes the world actually flew: Boeing Commercial Airplane, Douglas Aircraft, and Lockheed. The objective was crisp and pragmatic: deliver both the technology and the confidence manufacturers would need to commit to composites on future airliners. Technology meant design concepts and manufacturing processes that scaled without devouring budgets. Confidence meant demonstrating that these parts could be certified by regulators, accepted by airlines, and proven in service. Behind those words glimmered the metric everyone cared about. Cut aircraft weight by roughly a quarter and you could save 10 to 15% in fuel. Engineers knew where the largest savings hid: in the wings and fuselage, the places that carry most of an airliner's mass. But those were also the most sacred territories from a safety standpoint, and prudence prefers steps to leaps. So the program began where loads were lower and the stakes, though real, were less existential. Secondary structures came first. If these succeeded, more ambitious components would follow. The upper aft rudder on the Douglas DC-10 became an early testbed. This movable surface, hinged at the trailing edge of the vertical tail, helps coordinate turns and trims the aircraft if an engine is lost. Work on composite versions had begun in 1974 and folded naturally into the broader energy efficiency effort. 12 rudder units went into service. Engineers calculated that after 50 to 100 such units, the manufacturing cost would undercut metal. The weight savings were immediate and clear: a 26.4% reduction compared to the traditional aluminum alloy. Elevators were next. Mounted on the trailing edge of the horizontal tail, they control the airplane's pitch. 10 composite elevator units were designed for the Boeing 727, with flight testing beginning in March 1980. The numbers told a promising story. With a 23.6% reduction attributed to the elevator assemblies, Boeing judged the effort a success and approved composite elevators for the then-new Achan 757 and 767. Then came inboard ailerons, the control surfaces near the inner sections of the wings that, together with the rudder, bank the airplane during high-speed maneuvers. Installed on a Lockheed L1011, 8 composite ailerons entered flight testing in 1982. Their advantages could be counted like coins: 65 pounds trimmed away compared to aluminum, the number of ribs reduced from 18 to 10, and the forest of fasteners thinned from 5,253 to 2,564. In sum, these 3 secondary structures, rudders, elevators, and ailerons made from graphite epoxy, tipped the scales at about 1,500 pounds altogether and delivered a combined weight reduction of roughly 450 pounds compared to aluminum parts. Buoyed by those results, the program moved deeper into the airframe with what it called medium primary structures: the vertical fin, horizontal stabilizer, and vertical stabilizer. These were not secondary. Other components attach to them and they anchor the aircraft's stability. The vertical fin at the back of the airplane contributes to directional steadiness in the yaw axis. For the Lockheed L1011, a composite vertical fin was designed starting in 1975 and brought under the energy efficiency umbrella in 1976. The structure measured 7 by 23 feet and weighed around 780 pounds. The theoretical reward was significant, a 22.6% weight savings, yet reality, as ever, demanded proofs. In static testing, the composite fin failed before reaching its ultimate load and never progressed further within the program. A disappointment, yes, but an instructive one. The composite horizontal stabilizer, a fixed surface at the tail that provides longitudinal stability, followed. This one was designed for the Boeing 737. Ground tests revealed structural failures. Engineers corrected them. In August 1982, the Federal Aviation Administration certified the component. On April 11, 1984, a milestone quietly arrived. The first composite primary structure went into airline service, carrying with it a 28.4% weight saving. Finally, the program turned to the composite vertical stabilizer for the Douglas DC-10, the surface that controls yaw. It promised a 22.1% weight reduction, but encountered production troubles and a failed ground test along the way. After redesign and more time than planners had hoped, the FAA certified the part in 1986 and commercial service began in January 1987. As the structures grew more ambitious, the tools for thinking about them grew more sophisticated. Langley engineers wrote software to help design and analyze composite parts. Pasco assessed panels and guided choices about material strength. Vipasa worked alongside it, calculating buckling and vibration behavior. Conmin, a nonlinear mathematical optimizer, handled sizing problems. 3 years further on, Postop arrived to study panels under compression, shear and pressure, taking into account the way temperature tugged at each property. Not every question could be answered on a screen, of course. Traditional analysis and hands-on experiments, those carefully designed failures that teach designers where the cliff edge really lies, remained at the core. If a crack appeared, how did it spread through a laminate, and what did that mean for safety margins? If a tear occurred, how could it be repaired on the line with confidence and clarity? Teams built repair methods to match the new materials. They also looked beyond structural loads to the long, slow theatre of weather and time. Would sunlight degrade the resin over years? Would moisture sneak in and weaken the bonds? Panels were mounted on rooftops at airports from Langley to San Diego, from Seattle to Sao Paulo and Frankfurt. The tests tried to reflect the world as aircraft actually met it. Different latitudes and seasons, varying solar heating, ultraviolet exposure, and temperature cycles. Flight tests added another dimension. After 3 years, the program's leader at Langley, Richard A. Pride, could report that no significant loss in residual strength had been observed. Longer studies, stretching out to a decade, suggested that, under normal use and exposure, the composites held their strength. And yet a different sort of environmental concern threatened to halt everything, briefly grounding composite flight tests. The worry wasn't about what happened to the airplane, but what might happen to the world below in a worst-case accident. Carbon fibers conduct electricity, and in composite parts they are a principal ingredient. If a crash or explosion released fibers into the air over cities or towns, could those fine strands travel on the wind and short out electronics on the ground? Televisions, toasters, computers, even air traffic control equipment, or, in the darkest scenarios, elements of nuclear power plants. The fibers were feather light and in a violent release might be scattered widely. Moderate winds could carry them tens of miles. If damage occurred, who would be liable for replacing the spoiled equipment? To confront this, the program launched a major investigation: the Carbon Fiber Risk Assessment. At Langley, Robert J. Houston led the work as program manager of the Graphite Fibers Risk Analysis Office. The studies were exhaustive and, importantly, quantifiable. The conclusion, after the dust of analysis settled, was that the risk would be negligible. The predictions came with numbers that felt almost unreal in their smallness. Out of 100 televisions exposed, a handful of thousandths might fail. Toasters fared in the same untroubling range. For critical systems, the fraction was still small. A few thousandths out of 100 for air traffic control devices, a bit more for ground computer installations. Across more than 50 technical reports, NASA projected damages that, even in conservative accounting, were tiny, on the order of $1,000 in a year like 1993, and set a worst-case scenario in which a much larger loss might occur once in tens of thousands of such exposures. Set beside other threats in aviation, carbon fiber fallout faded into the background. This pause and proof had a cost, however, and time in research is a currency you never get back. The Composites program, which ran from 1976 to 1985, reached its twilight before it could deliver full composite wings and fuselages. The very target that offered the richest harvest, because wings and fuselage together make up roughly 3/4 of an airliner's weight. Those structures held the promise of profound savings, but the detour into risk assessment consumed resources that planners had not foreseen. When the path cleared in 1981, NASA changed tactics. Instead of replacing entire metal assemblies, engineers incorporated composite sections into larger structures. A fuselage barrel here, a short-span wing box there. Boeing studied how composite wings would tolerate damage, what lightning strikes would mean in service, and whether fuel tanks sealed as well as tried-and-true metal designs. Lockheed examined how sound moved through flat, angular composite panels and how best to hush it. Yet the clock ran out. Funding and time dwindled, and the vision of full composite wings and fuselages remained beyond the horizon. Even so, the gains were far from modest. The achievements in secondary structures were called almost revolutionary, and more than one voice later described those 10 years as a golden age for composite research in the United States, with the energy efficiency program as its strategic center of gravity. Across its life, the composite effort produced around 600 technical reports, established cost frameworks for development and production, and perhaps most importantly, hardened confidence in durability and long-term use. Regulators granted certifications. Airlines, known for their sturdy skepticism, accepted the parts. Langley continued to track how the components behaved in the field even after the program wound down, and by 1991 some 350 composite components had accumulated 5.3 million flight hours and remained in service. Looking back, one of the program's original task force members put it simply: many of the things engineers debated then are now so standard that people forget where they came from. Before the energy efficiency effort, manufacturers had been reluctant to explore composites deeply. Costs loomed. Performance was unproven. Afterward, composites became a major aspect of commercial transports, paying off in the coin that matters most in flight: weight, and therefore fuel. By the 1990s, the materials were credited with fuel efficiency gains in the double digits, around 15% in some assessments, and a consensus began to form. The program had given manufacturers, regulators, and airlines not only data, but experience, the kind that makes future choices feel less like leaps and more like steps. If you enjoy drifting through this kind of calm, fact-rooted history, take a moment, without breaking your rhythm, to like and subscribe to Space Historian. It helps these gentle journeys continue, and it means you can return any night and pick up the thread. After the formal end of the program, Composites kept spreading, though not as dramatically or quickly as early dreams had sketched. The arithmetic of production costs and the extra caution and expense of certifying new materials for flight slowed the march. Still, as fuel prices rose in the new century, the economics tilted back toward lightness and efficiency. In military aviation, Composites surged ahead faster than in commercial fleets. An advanced fighter like the F-22 carried a notable fraction of its weight in composites, well over a third. In contrast, the most composite-rich large airliner of that time, the Boeing 777, sat closer to a tenth by weight. Even so, a new generation beckoned. Boeing 787 Dreamliner, in its planning, promised to tip the balance decisively, targeting roughly half of its primary structures, fuselage and wing alike, in composite materials. Smaller aircraft felt the wave too. General aviation designers, including the inventive Burt Rutan, took to composites with gusto. Personal and home-built types showcased the shapes and efficiencies the materials made possible. In business class and light aircraft, manufacturers pursued all composite designs, and the catalogue of examples grew to include models like the Langley Columbia 300 and the Cirrus SR20. By the time the energy efficiency work at Langley hit its stride, something subtle had shifted in the mood of the industry. The new materials no longer felt like museum curiosities. As one aviation writer noted with relief, that long, anxious pause, the fear of the unknown, had been shattered. Composites had stepped out of the laboratory and into everyday transport aviation. What began as an experiment became a working practice. A historian of NASA's aeronautics would later sum it up this way: the program's steady, methodical progress didn't just invent tools, it accelerated acceptance, and it did so in the best spirit of partnership. Ideas conceived, matured, and handed across to manufacturers at just the right time, in a professional way that invited trust. If this calm, fact-woven journey helps you unwind, consider a gentle nudge. Subscribe and like Space Historian so you can drift back to stories like this whenever your evening needs a soft landing. There was another branch on this family tree of fuel saving, one with a broader scope and a satisfyingly practical title: Energy Efficient Transport. The name was chosen somewhat arbitrarily, two Langley engineers admitted, but the intent was clear. Where the composites effort focused on a single technological domain, EET reached across a suite of aerodynamic improvements. It, too, was run from Langley and promised benefits that manufacturers could count. The work would touch supercritical wings, winglets at the tips, the flow around engine nacelles and the loads they endured, new coatings for wings and tails, the taming of boundary layers to keep air smooth and laminar, and finally, active controls. Those quick, clever systems that let computers shoulder some of the burden of keeping an aeroplane in its best state. As before, the partnerships were practical. NASA's Langley team working with Boeing Commercial Airplane, Douglas Aircraft, and Lockheed California to analyze, design, test, and crucially, assess what truly paid off. Most airliners cruise in a region that has long teased and troubled aerodynamicists: the transonic band. Think of it as the mingling zone between subsonic and supersonic flow, roughly from Mach 0.8 to Mach 1.2. Even when an aircraft is officially subsonic, bits of air rushing across its wings can briefly slide into supersonic speeds and then slam back down across a shock, like water tumbling over a ledge and foaming white. Each shockwave is a tax on efficiency, a spike in drag that steals fuel. In the late 1940s, the barrier was beaten with raw power. The challenge now was refinement. Cross that threshold quietly, keep the shocks weak, and harvest the savings at cruise where airlines live. Langley's Richard Whitcomb had been peering at this puzzle since the 1960s, sketching, testing, reshaping the wing profile itself. After years of wind tunnel work, he flattened the upper surface to take the teeth out of those shock waves and curved the trailing edge downward to encourage lift. The shape looked unconventional, almost wrong to eyes trained on classic airfoils, yet it worked. The beauty of the idea was practical as well, because the supercritical wing could be thicker at a given performance level. Engineers could lengthen and narrow the wing planform to improve its aspect ratio and reduce drag further, while also relaxing the sweep angle for a more efficient cruise. In 1972, after a dozen test flights had traced these expectations into the air itself, Whitcomb felt they'd reached a milestone. The supercritical wing had become not just a drawing, but a path forward. The fuel crises provided the incentive to move from proof to adoption. EET folded the supercritical concepts into its core work, building a database in tunnels and on wings that explored thickness, camber, sweep, and aspect ratio with a librarian's thoroughness. Industry followed. Boeing introduced supercritical features on the 767 in 1981 and refined the idea even further on the 777 in 1995, a wing some would later call the most efficient subsonic airfoil then flying. It was a straight line from Whitcomb's first quiet curves in the tunnel to the wings that carried passengers across oceans with less fuss and less fuel. Whitcomb had a second idea that moved just as gracefully from imagination to hardware. In 1974, he began exploring winglets, upright tips like small sails that sit in the invisible whirlpool at the wing's end. Where the supercritical wing promised most of its savings on future designs, winglets offered something irresistible in the short term. They could be retrofitted. In July 1976, Whitcomb published his findings and forecast a drag reduction in the range of 4 to 8%. He said it as simply as he could: expect to see them on the next generation of airliners, as dependable as dawn. The exact shape would vary from aeroplane to aeroplane. Each wing has its own vortex signature, so manufacturers were encouraged to tailor and test. To speed the shift, NASA and the EET project co-sponsored flight tests. Between 1978 and 1979, Douglas trialled winglets on a DC-10. The result was hard to ignore: less fuel used for the same mission. Douglas soon incorporated winglets into the MD-11 development in 1986, and the rest of the industry, seeing the returns, moved quickly to make the new tips their own. Cutting drag in smooth air was one challenge. Keeping an aeroplane both light and resilient in rough air was another. Reinforcements to meet flutter and gust loads can add weight fast. One answer, much discussed, occasionally doubted, and then proven, was active controls technology, sometimes called control-configured vehicles. The principle is that a fast, dedicated computer can sense disturbances and adjust control surfaces more quickly and more precisely than a human pilot reacting alone. Sensors on wings and tails feed measurements into the system. Within fractions of a second, the computer commands rudders, elevators, and ailerons to counter the gust or the onset of flutter, holding loads down while maintaining safety margins. Before the energy efficiency push, some worried these systems would cost too much or prove too complex to be worth their weight. Langley's engineers worked with Douglas, Lockheed, and Boeing to show otherwise. The return on investment arithmetic looked compelling in the early 1980s. An outlay on the order of $600,000 with an expected 25% return based on contemporary fuel prices. Regulators reviewed the safety case and concluded that the systems were flight-worthy and robust, designed so that no single failure could wrest control from the crew. When Pan American World Airways took delivery of an L1011-500 with active controls and began retrofitting the rest of that type in its fleet, the idea had crossed the line from theory to operational practice. Another strand of EET's tapestry lay where air meets engine. The Nacelle Aerodynamic and Inertial Loads (NAIL program, run jointly by Langley and Lewis Research Centre, looked closely at how engine efficiency ebbs in the early life of a power plant. Data suggested that the steepest deterioration happens in the first 1,000 flights, then levels off. The goal was to gather enough detailed information in that early period to understand why. Working with Boeing and Pratt & Whitney, the team built a NAIL engine, flew it, took it apart, and studied the wear patterns. The flights revealed that the toughest loads came at low speed with high angles of attack and heavy airflow, precisely the regime of takeoff. Those findings fed back into nacelle design, helping future inlets and housings better withstand the wear and tear of that intense, repeated phase of flight. Two more EET efforts overlapped with other energy efficiency work. One was a look at how coatings might make wings and tails a little slicker and a little more durable. The Apollo program had used Captain, a polyamide film, for thermal protection. It also offered drag and maintenance benefits. Langley engineers examined elastomeric polyurethane coatings, materials like Kea-Apco and Chemglass, and tested them on a Continental Airlines 727 operated by Air Micronesia. The Micronesian climate, with its frequent rainfall, was ideal for seeing how well coatings stood up. The findings were modest but meaningful. A small reduction in drag paired with better protection against corrosion. One question remained open at the time: how would such coatings perform on larger, more curved wing-like surfaces where the flow and the geometry are more complex? The other overlapping strand involved laminar flow, the dream of keeping the boundary layer of air smooth and unruffled across a larger portion of the wing to reduce drag. Within EET, teams pursued natural laminar flow studies that yielded encouraging results. In analysis, a 757 achieved significant stretches of laminar flow on a Mach 0.8 flight covering roughly 2,400 miles, turning a long cruise into a lesson in gentle efficiency. By the time the EET work had matured, it had generated nearly 150 technical reports, a quietly impressive library that captured what had been tried, what had worked, and why. Read together, they delivered a confident forecast. New airliners built with these ideas could achieve fuel efficiency gains on the order of 15 to 20% over the models then in production. One of the early leaders of the broader energy efficiency effort pointed to the most visible fruits: winglets capping the tips, supercritical wings shaping the cruise, and active controls trimming away structural penalties the moment the air turned bumpy. On the whole, the advanced aerodynamics side of the program had done what it promised. There was, however, an irony in the way ideas travel. Some of these fuel-saving advances seemed to spread faster in Europe. One Langley manager recalled sitting aboard a French-built Airbus A310 on the ground, glancing out and spotting a winglet at the tip. Smaller American business jets had worn them first in the United States, but this was his first sighting on a large commercial transport, the very class of aeroplane where winglets make their largest economic mark. He remembered too that Israeli designers had been early adopters on the West Wind. The conclusion stung a little. In his personal experience, European firms might have capitalized more quickly on the program's results than some American companies. This was not a trivial worry. From the start, Langley managers had flagged a broader strategic concern: The United States' long-standing dominance in large civil aircraft manufacturing faced a real challenge. By 1982, Eastern Airlines had bought 34 Airbus A300s, lifting Airbus into second place internationally, ahead of Douglas and Lockheed. The competitive landscape was changing. Even so, there was reason for measured confidence. Both the EET and Composites programs were already returning tangible fuel savings, and fuel efficiency, many believed, would continue to drive airline purchasing decisions around the world. On the propulsion side, colleagues at NASA's Lewis Research Center in Cleveland pressed forward with their own innovative projects to push fuel use down even further. The aerodynamic and materials gains now matched by improvements in the engines that turned air into thrust, all of it pulling in the same direction. A quieter, leaner cruise that sipped less of a precious resource and carried more of the future in its wings.